Good day and welcome to our online class. Our subject, pre-calculus, is divided into three chapters: the analytic geometry, sequence, series, and mathematical induction, and trigonometry. This video will be the first lesson for analytic geometry. Supposed to be, analytic geometry begins with the study of points, distance between points, lines, and their equations on a rectangular coordinate system. But these topics have already been discussed during your previous classes in high school. The analytic geometry in our class will focus on conic sections, and so we begin with the overview of conic sections. Unknowingly, you may have been encountered conic sections in your daily lives. Circle, which is one of the first shapes we've learned, is a conic section. When you throw a ball at an angle above the ground, the trajectory of the ball is a parabola, which is a conic section. The orbit of planets around the sun is an ellipse, which is, again, a conic section. But how are conic sections formed? If you have a double-dapped cone or a double cone, or two congruent right cones with common vertex configured as shown in the image, and you pass a plane through these cones, the intersection of the figures form conic sections. As you can see, the type of conic section formed depends on the way you pass the plane through the cones. When you pass a plane parallel to the side of the cone, a parabola is formed, which can be seen in the leftmost figure. When you pass a plane perpendicular to the axis of the cones or parallel to the bases of the cones, a circle is formed. When you pass a plane at an angle or a plane that is not parallel to the sides nor perpendicular to the axis, an ellipse is formed. And when you pass a plane parallel to the axis of the cones, thus intersecting the cones simultaneously, a hyperbola is formed. There are also other conic sections called degenerate conics. If the plane passes through only at the common vertex of the cones, a point is formed. A straight line is formed if the plane is tangent to the double cone's surface. And a pair of straight line is formed if the plane passes through the vertex and intersects both the top and bottom halves of the cone. If we are going to draw these conic sections, including the degenerate conics and a rectangular coordinate system, we determine the equation of these conic sections that may define the conic sections themselves. And all of these conic sections, including the generic conic sections, have a general equation in the form of ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0, where the coefficients are all real numbers and coefficients a, b, c, or the leading coefficients, are not all 0. There is one particular note that we have to consider. If the coefficient b is 0, that is, xy term is missing, the resulting conic section has an axis parallel to one of the axes of the rectangular coordinate system, or is parallel to the x-axis or parallel to the y-axis. However, if the coefficient b is not equal to 0, and that is we have an xy term, the conic section formed will have an axis which is inclined or forms an angle with the axis. With these types of conic sections, we are going to rotate. We are going to rotate our axis, and thus we are going to be facing more complex equations. And thus, for the simplicity of our lesson and for the purpose of our discussion, we are only going to deal with um, conic sections with general equations that do not have an xy term, that is, b is equal to 0. And thus, we may define, for the purpose of our discussion, a new general equation which is free of the xy term, which is ax squared plus by squared plus cx plus dy plus e equals 0. Interestingly, from our general equation itself, we can or we may know what type of conic sections are we dealing with. Just by inspecting the coefficients a, b, c, d, and e. If a equals b and both are not equal to 0, the equation may be of a circle. If a is not equal to b but they have the same sign, the equation may be of an ellipse. If a and b have opposite signs, it doesn't matter if they are equal or not, the equation may be of a hyperbola. And if a is equal to 0 or b equals to 0, that is, if only one term has a second degree, then the equation may be of a parabola. Okay, sorry. For the general equation in number 1, by inspecting through its coefficients, we can see that a and b, or the coefficients of x squared and 4 squared, are equal and the same in sign. Therefore, our first equation is an equation for a, or the general equation for a circle. For number 2, a and b are not equal, that is, the coefficient of x squared is 1 and the coefficient of y squared is 2, but they have the same sign. Therefore, our equation 2 represents an ellipse. For equation number 3, a and b are not equal and they have opposite signs. That is, a, the coefficient of x squared is 5, which is a positive sign, and b, the coefficient of y squared is negative 6, which is the opposite sign of a. Therefore, our third equation represents a hyperbola. Our last equation contains only one second degree term. Therefore, the fourth equation represents a parabola. This method of determining what type of conic section is represented by the general equations is not always correct, because as you remember, the general equation is also shared with the generate conics. That is, we are not actually 100% sure that our assumptions based on inspecting the coefficients are correct. They are not always correct. And so, what are we going to do? We are going to transform the general equations into a standard form that is specific to each conic section, which will distinguish it from the generate conics. The standard form or the standard equation for a circle is the quantity of x minus h squared plus the quantity y minus k squared equals r squared, where the h and k is the center of the circle and r is the radius of the circle. The standard equation for an ellipse is x minus h squared all over a squared plus quantity y minus k squared all over b squared equals 1, where h and k is the center of the ellipse and where a and b are the lengths of its axis. So for now, let's not be bothered by the letters or the variables or the constants a, b, h, and k, because on the succeeding discussions, we are going to talk about each conic section. So we will know what are these variables or constants for. So for now, what we are required to know to is to learn these standard equations which are distinct or specific with each type of conic section. Or the standard equation of an ellipse may also be like this: the quantity of y minus k squared all over a squared plus x minus h squared all over b squared equals 1. Again, please don't be bothered by the variables a, b, and h, k, and why are they interchanged, and why does it have two standard equations, because I will explain it in the succeeding discussions. For parabola, the general equation will be 4a times x minus h equals the quantity of y minus k squared, or 4a times y minus k equals the quantity x minus h squared. For a hyperbola, the equation will be, the standard equation is the quantity x minus h squared all over a squared minus the quantity y minus k squared all over b squared equals 1, or the quantity y minus k squared all over a squared minus the quantity x minus h squared all over b squared equals 1. So those are the standard equations specific to each type of conic sections. How about the generated conics? Do they have a standard equation? The generic conics can be determined if the equation of a circle, the standard equation of a circle, or an ellipse has a constant equal to 0, or that is the right hand side of the equation becomes 0, then the equation represents a point. It represents a line if either side of the standard equation for the parabola is 0. And it represents a pair of intersecting lines or a pair of straight lines if the right hand side of the standard equation for a hyperbola is 0. In that way, you can distinguish the degenerate conics from the conic sections or the conics themselves. So what are these standard equations for? If you are given a general equation, all you have to do is reduce or transform the general equation into their standard form and inspect if it falls within which type of conic section or degenerate conics. Let's have an example. Okay, for number 1, we are given 6x squared plus 6y squared plus 12x minus 24y plus 12. So if we use a method of
inspecting the coefficients, we can see that the coefficients of x squared and y squared are the same, and they are equal in sign, or they have the same sign. So we can assume that this equation represents a circle. But to be sure, we have to convert this general equation of the Conic section to a standard form. Okay, we do this by first we collect all the terms with the same variable. So we have 6x squared plus 12x, then plus 6y squared minus 24y, and then transpose positive 12 on the right hand side or right side, and we get negative 12. But before going any further, notice that all of the coefficients of the equation are divisible by 6. So I am going to divide the whole equation by 6, and I will get x squared plus 2x plus y squared minus 4y equals negative of 2. Okay, to make this equation in standard form, I am going to complete the square, because as you can see, all of the standard form contains perfect square trinomials, or expressed in a square of a binomial. In order to do that, I would complete the square in each variable, complete the square in x and complete the square in y. And how do we complete the square? First, okay, we add a constant term that would complete the square for each variable. And what we have added on the left side should also be added on the right side. To complete the square, since the coefficient of x squared is 1, we can divide the second term, the coefficient of the second term, 2x, which is 2, divided by 2. So 2 divided by 2 is 1. And then we square the answer. So 2 divided by 2 is 1, and 1 squared is 1. So we add 1. Then, same is true for the y variable. So we have y squared and minus 4y plus negative 4 divided by 4 is negative 2, and negative 2 squared is positive 4. Then we add to the right side 1 plus 4, which is what we've added on the left side. And now we have already completed the square. X squared plus 2x plus 1 can be simplified to x plus 1 squared, and y squared minus 4y plus 4 can be simplified to y minus 2 squared, which is equal to negative 2 plus 1 plus 4 is equal to 3. So, as you can see, this equation resembles the standard equation of a circle, which is x minus h squared plus y minus 2 squared equals r squared. Okay, to make it clearer, you can rewrite 3 as a square. So in order to do that, you may rewrite it into square root of 3 squared. Therefore, the equation 6x squared plus 6y squared plus 12x minus 24 plus 12 equals 0 can be converted into the standard form of a circle with radius square root of 3 and a center of negative 1, positive 2. Therefore, our assumption is correct. The general equation represents a circle.
For our number 2, we have 2x squared plus y squared minus 4x minus 2y minus 1 equals 0. So here, by inspection, we have the coefficients of x squared and y squared are not equal, but they have same sign, so I assume it's an ellipse. But to prove it, we have 2 reduce the general equation or transform the general equation into a standard form. So what we're gonna do again is to complete the square. First, okay, collect all terms with similar variables. Then, okay, transpose the constants to the right hand side. So negative 1 would become positive 1. Next, to complete the square, we are going to have to add, okay, constants on both sides. However, for this particular equation, for the terms with variables or x variables, the coefficient of x squared is 2. So what I'm going to do first is to factor out 2. And then I will be left with here negative 2x. Then I would add space for the constant term added, or what, to complete the square. Then for the variable y, or y variable, I am not going to factor it because y squared has a coefficient of 1. So this is just the same as our first problem or equation. Now what I'm gonna do is to complete the square inside the parentheses. So we have x squared minus, I'll divide negative 2x by 2 and I'll get negative 1, and negative 1 squared is positive 1. So the constant term to be added is positive 1. Next, y squared minus 2y, negative 2 divided by 2 is negative 1, and negative 1 squared is positive 1. Okay. How about on the right hand side? Okay. This time, because I have factored out 2, okay, when in fact what I've added is 2 times 1. Okay, I should add plus 2 here. I should add 2 on the right hand side and not 1, because remember, you factored out 2. And if you simplify these terms, you'll know that the constant term added is positive 2 and not only 1. Okay, this is one of the common mistakes of students. Instead of multiplying the factored out constant with the added constant in completing the square, they only added the constant inside the parentheses. So that is wrong. Okay, if you factored out a constant to complete the square inside the parentheses, you should multiply by 2 or by any constant that you factored out. Then for the y variable, no factoring. So just add 1 because that is what we added on the left hand side. Now, inside the parentheses, the term inside the parentheses is a perfect square, and it reduces to, or it simplifies to, x minus 1 squared. And the same is true with y squared minus 2y plus 1. It would simplify to y minus 1 squared, which is equal to 1 plus 2 plus 1, you get 4. Okay, clearly it is not a circle because you have a factor here, a constant term outside the parentheses. So I'm going to divide all of the terms by 4. Because in the standard form, remember, this 4 is a perfect square. So you might say it is r squared. It is a radius, then it should be a circle. But remember, the standard equation for a circle is x minus h squared plus y minus k squared equals r squared. There is no constant term here. But in this example, we have a 2. So it is not, clearly, it's not a circle. However, for an ellipse, we have x minus h squared plus y minus k squared. I'm sorry, h minus h squared over a squared plus y minus k squared all over b squared equals 1. The right hand side should be 1. I have 4. So what I'm going to do is I'll divide all of the equation by 4. Okay. Then it will simplify to x minus 1 squared divided by 2 over 4 is 2 plus y minus 1 squared all over 4, which is equal to 1 because 4 divided by 4 equals. So by, I'll write it at the top. By rewriting the equation, okay, I can get an equation which is a standard equation of an ellipse. I'm sorry. So my final answer, the equation 2 represents an ellipse because its standard equation is that of an ellipse. Let's move on to number 3. The equation is 4x cubed x squared minus 3y squared minus 8x plus 24y minus 8 equals 0. By inspection, the coefficients of x squared and y squared are not equal, but they have opposite signs. So I assume they are hyperbola. To prove or disprove it, we should rewrite it to standard equation. Again, collect similar terms with similar variables. Minus 3y squared plus 24y, then transpose the constant to the right side, sorry. And again, the coefficient of x squared is not 1, so you have to factor out that coefficient. Then negative 8x would become negative 2x, and then we add some constant term to complete the square. The same is true for the variable y variable. So we have factor out negative 3, we simplify to y minus squared minus 8y plus some constant variable or some constant to complete the square equals 80. Then what we added on the left side should also be added on the right side. Now we complete the square of the terms inside the parentheses. We have x squared minus 2x divide negative 2 by 2, that is negative 1, and square negative 1, we have positive 1. Minus 3 times y squared minus y plus divide negative 8 by 2, that is negative 4, and negative 4 squared is 16. Okay, and then we add, remember, if you factored out some constant, you multiplied the added constant term to the factored outside before adding it on the right hand side. So we have 1 times 4, we should add 4. And for this, we should have, for the y variable, we should add 16 times negative 3, that is negative 48. Okay, so the terms inside the parentheses would become a perfect square, and it simplifies to x minus 1 squared minus 3 times y minus 4 squared. And the right hand side would become 80 plus 4, 84 minus 48. That is equal to 36. So if it is a parabola, the right side should be 1. So I'll divide it again by 36. And
This simplifies to x minus 1 squared divided by 4 all over 36, that is 1 all over 9, and 9 is 3 squared, plus, or sorry, minus y minus 4 squared. 3 all over 36 is 1 all over 12. And that simplifies to the square root of 12 squared. 36 over 36 equals 1. So you may be wondering, why did I wrote 4 over 36 or 1 all over 9 in the form of 1 all over 3 squared, and same is true with 1 all over 12. I express it in terms of squares because the standard equation for the hyperbola requires it that the denominator should be expressed, or should be a square. And so from here, by inspection, we can see that equation 3 really represents a hyperbola. Okay. For our last problem, we have x squared plus 8x plus 4y plus 36. By inspection, we see that only one term has a second degree. And from our method a while ago, by inspecting the coefficients, we can assume that it's a parabola. Okay, and to check if it is true, we should again transform this general equation into a standard form. Okay. Parabola is much easier because instead of completing squares in two variables, we only need to complete the square in one variable, and that is the variable with the second degree. In this case, we only need to complete the square of x squared plus 8x because it is the only variable with the second degree. Everything with other variables, or everything including constant and the variables of y, would be transposed on the right hand side, and this would become positive 4y minus 36. Then we proceed on completing the square of the left hand side. We add a constant term to complete the square, and to be sure that we are not violating any mathematical law, what we added on the left side should also be added on the right side. So to complete the square, we add 8 divided by 2 is 4, and 4 squared is positive 16. Then we also add positive 16 on the right side. The left side would simplify to x plus 4 squared, and the right side would simplify to 4y minus 20. The standard equation for a parabola is x minus h squared equals 4a times y minus k. So as simplify the equation further, since I have to factor out 4a, in this case, I have to factor out 4 and y minus 5. So, sir, you are, maybe you are wondering, sir, you don't have a. A is any constant here. So, in this case, RA is 1. Yes. Okay. It may be omitted, but it's there. A is 1. And thus we factor out for A there. And so we prove that question number 4 represents a parabola because they have the standard form corresponds to the standard form of that of a parabola.
what if we have a what if it's the other way around? We are given the standard form and we convert it or we transform it to its general form. I think it's more easier because we what we are only going to do is to expand the binomial or the square of the binomial and also eliminate the fractions if possible. So we have x minus 3 squared all over 9 minus y plus 4 all over 4 squared equals 36 equals 1. To eliminate, I'm sorry, the square should only be in the numerator. To eliminate the denominator, the greatest or the least common multiple of 9 and 4 is 36. So I am going to multiply both sides of the equation by 36. And from there, 36 all over 9 would give us 4 multiplied to the square of the binomial x minus 3 and minus 36 divided by 4 is 9 multiplied by the square of the binomial y plus 4 and 36 times 1 on the right side would be 36. So before we distribute the constant term or the constant factors, we first expand the binomial. And by expansion, it would become x squared minus 6x plus 9 minus 9 times y squared plus 8y plus 16 equals 36. And this simplifies to 4x squared minus 24x plus 36 minus 9y squared minus 72y minus what's 9 times 16, that is 144. And I will now transpose 36 on the left hand side, so it becomes negative 36 equals 0 because the general equation requires us that the right hand side should be 0. And now we are done. We are just going to rearrange the equation and combine like terms if necessary, add the constant terms. Since I don't have any more space, I'll write it above. So we have 4x squared followed by minus 9y squared followed by 24x. Sorry for that. And then followed by minus 72y. Then let's simplify. Plus 36 minus 36, that is 0. And so we are left with negative 144 equals 0. So this is the general form of the given standard equation, which is a hyperbola. So that's all for the overview of conic sections. So just to summarize, what we have learned today is that we define conic sections and also the generate conics. We learned about the general equations, the general form or general equations of conic section or conics. And then from there, we also learned how to transform the general equation into standard form for us to be able to determine what type of conic sections or the generate conics the equations are representing. There is what we call a method of by inspecting the coefficients in a general equation of a conic section, where you can not always true, but you can determine the type of conic section by inspecting the coefficients. But the more precise and accurate method is to transform the general equation into standard form. Why? Because each conic section, including the degenerate conics, has its own or its specific standard equation. So I hope you learned something from here and see you on the next lessons. If you have any questions, feel free to contact me. Thank you and good day.